So after discussing intermolecular forces, that was like van der Waals force, also known as IDID force, also known as temporary dipole, okay, also known as Gundon forces, also known as dispersion forces. Then we have discussed like the permanent dipole, and then we have discussed hydrogen bonding. So these are the questions related to intermolecular forces. This is a question about water. Water might be expected to have a lower boiling temperature than hydrogen sulfide, but it actually has a higher boiling temperature. Comment on this statement by referring to the IMF in both these substances. A detailed description of how the intermolecular forces arise is not required. So just try this question. So H2S, like hydrogen sulfide is H2S, and this is water. This is water. So you have first decide that they are saying water might be expected to have a lower boiling temperature, okay? Then H2S, then H2S. So like what you are supposed to write then? One thing is very interesting in this question, okay, have a lower boiling temperature than hydrogen sulfide, but it actually has a higher boiling temperature, right? Because I told you intermolecular force, I told you intermolecular force is directly proportional to the number of electrons. Intermolecular force is directly proportional to the number of electrons, or you can say the number of atoms.
In hydrogen sulfide, the number of electrons, IMF is more in hydrogen sulfide
is higher. Exactly. If I ask how many electrons are there in water and how many electrons are there in hydrogen sulfide, so in water I would say that there are 18 electrons. Am I right? There are 18 electrons.
Yes.
No, sorry, 10 electrons. There are 10 electrons because
10.
the proton number for oxygen is 8. The proton number for oxygen is 8, right? And the proton number for hydrogen is 1. So there are 2 hydrogen atoms in water. So 2 plus 8 would be equal to like 10 electrons. And then if we discuss H2S, that is, you can say
18.
2 electrons, and then sulfur is 16. So the total is 18, right? So
Yes,
ideally it must have the strong IMF, and it has a low IMF. Okay, it has a low IMF, right? So so you can say that water is expected to have a lower temperature. Water is expected to have a lower temperature. Water is expected to have a low boiling temperature. Low boiling temperature, okay, because water has fewer electrons.
the question is saying that water has a high boiling point than H2S, right?
Exactly. So we would lead to that statement, but we have to explain this, right? Okay, why they have
Sir, water
like
also
mentioned
has
that.
hydrogen bonding.
Exactly, yes, water also has hydrogen bonding, so that's why it has a higher boiling temperature finally. So due to this, I can say that water has less number of electrons as compared to the H2S. So water might have weak London forces. Water has weak London forces. Water has weak London forces. Okay. So
Yes, sir.
London forces. Okay. But the thing is, water contains hydrogen bonding. But hydrogen bonding, that is more stronger than London force. Okay, London force.
Yes, sir.
Hence, more energy required to overcome hydrogen bonding. This is the reason water is having the higher boiling temperature. Okay, are you getting my point?
Yes, sir.
Now, see this question.
Because there's no hydrogen bonding.
Hydrogen bonding, yes, exactly. There
There's
is
no
no hydrogen
hydrogen.
bonding in NCl3 and
Like
also in NF3.
we have to mention it in the
No,
answer. Like
no,
there's
no,
no.
no, 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 no. Because this is understood that there is no hydrogen bonding. So you only have the two types of forces. First one is the London force, that is like van der Waals force, or you can say temporary dipole. Another one is the permanent dipole. So if you can see, you have NCl3 and you have NF3. So as we know that the difference of electronegativity, obviously, if you go down the group, I'm talking about halogens. I'm talking about halogens. If you go down the group, electronegativity decreases or increases? Yes. Fluorine, then chlorine,
Fluorine, no.
then
Electronegativity decrease.
bromine, then iodine, then
It will
astatine.
decrease.
So if we go down the group, electronegativity decreases. Obviously, fluorine is more electronegative than chlorine. So the difference of electronegativity is lower. Am I right?
Yes, sir.
And the difference of electronegativity is higher. So it's more polar, I can say. It's less polar. Okay.
Yes, sir.
So when it's non-polar, it means that it has permanent dipole. Okay. And you can say, like if you have to do a comparison with respect to electrons, so can you tell me how many electrons it has? Like NCl3 has how many electrons? Yes.
17 electrons. Oh,
And
okay. In total,
Yes,
No,
totally.
wait. Chlorine?
Totally.
Or like 17 into 3 plus N?
Hmm.
Sir, wait, let me calculate. Sir, 58 electrons in total.
Okay, and then what about NF3?
34 electrons.
34?
34.
Oh, it means that NCl3 has a greater, you can say, van der Waals force, or you can say the London force. Okay, because NCl3 has more
Yes.
electrons. So, but the thing is that the dominant factor is the permanent dipole, right? Permanent dipole, you can say, permanent dipole is stronger than permanent dipole is stronger than the London force. So what they have told you that NCl3 has a boiling temperature of 344 Kelvin and nitrogen trifluoride has a boiling temperature of 144 Kelvin. Explain this difference in boiling temperatures by referring to all the intermolecular forces present. Yes. So obviously the number of electrons are greater in NCl3 as compared to the, you can say, NF3. Okay. So more number of electrons means more intermolecular force. More intermolecular force means it would be having a higher boiling
High boiling
temperature.
point.
As they have mentioned, this is 344 Kelvin. So 344 Kelvin is the dominant as compared to the 144. So then ultimately I can say that NCl3 has stronger intermolecular forces of attraction. Okay.
Yes, sir.
Yes. So finally, so finally, finally, London forces are greater in London forces are greater in NCl3 than NF3. Okay. Then so yes, I know that NF3 has a permanent dipole as the difference of electronegativity is higher. As the difference of electronegativity is higher, so if you can have, you can see, like what is the difference? Like you can say, what is the electronegativity of nitrogen? If you can see, chlorine is 3.0 and fluorine is 4.0. Okay, so like the electronegativity of, you can say, the electronegativity of nitrogen is uh, 3.04. Electronegativity of nitrogen is 3.04, right? 3.04. So I'm writing it down. Nitrogen is 3.04, and exact electronegativity of chlorine is 3.16. Chlorine is 3.16. Okay, and
Yes.
exact electronegativity of fluorine is 3.98. It's 3.98, which is approximately equal to 4. So if you are going to subtract electronegativities of the two different atoms, like NCl3 means nitrogen is 3.04 and chlorine is 3.16. So 3.16 minus 3.04 would be equal to what? 3.16 and 3.04. Yes. And also 3.1
Sir,
3.0.12,
0.12.
right? And if you can see this,
Yes.
it's 3.98 minus 3.04. So what's the difference?
0.94.
0.94, which is approximately equal to 1. Am I right?
Yes.
Yes. So that's why I can say that London forces are greater in NCl3, because if you can see 58 electrons and 34 electrons. 58 electrons and then you can see 34 electrons. So the London forces are the dominant factor in this question. So that's why I'm going to consider the London forces. Okay. So London forces are more
Okay,
significant.
sir.
So obviously more energy is needed to overcome. More energy is needed to overcome the force of attraction, in NCl3. So that's why I can say that it would be having the higher boiling temperature. Okay. Now see this question. Intermolecular forces.
Oh, okay, okay.
So like if someone consider that we have to look at intermolecular forces and then we would be like determining what's the boiling temperature, so they are completely wrong, because we have to consider just intermolecular forces. And I told you intermolecular force only depends on the number of electrons and the surface area, right?
Yeah, so chlorine has like less number of electrons, so IMF is less than iodine. Iodine has more number of electrons.
Yes, exactly. Iodine has a greater proton number as compared to bromine, and bromine is greater than chlorine. Chlorine is 17, and then bromine is larger than chlorine, and then iodine. So, like, what you would be writing in this question? This is of 2 marks only.
So we can just write down that chlorine has less number of electrons, so IMF, and chlorine has less number of electrons, and iodine has greater number of electrons, so IMF in chlorine is less than in iodine.
Okay. So, basically, it's down the group, right? It's down the group: chlorine, bromine, and then iodine. So, as you
Yes,
can
sir.
see, an
So
increasing
down the group,
temperature. Yes.
down the
So
group,
as we go down the
boiling
group, number
temperature
of
increases.
electron increases, right? Number of electrons increases. Okay. So, and then if the number of electrons increases, okay, so I can say that the strength of London force increases. When the strength of London force increases, so the more energy needed to separate the molecules. Why I am saying that more energy is needed to separate the molecules? Due to this. Basically, this is the London force between the molecules. This is a covalent bond. This is a covalent bond. This is a covalent bond. We're not supposed to consider the covalent bonds if you're going to melt or boil something else. It totally depends on the intermolecular force. So if the intermolecular force is the weaker, so you can separate the both molecules very easily. You can separate the both molecules very easily, just like that. But if you are thinking that intermolecular force is stronger, so it would be needed to give the higher temperature to the molecules so that they can be separated easily. So this is the reason I'm saying that if the intermolecular forces are stronger in iodine, so you will need a higher you can say energy to separate the both molecules. So this is the reason I am saying that the strength of London force are going to increase as you're going down the group. Okay. Hmm?
Yes, sir.
Yes. Okay. This is another question. See this. This is another question. The compounds hydrogen sulfide, chloride, water, and methane all have simple molecular structures, but they have significantly different boiling temperatures. Discuss the reasons for the differences in the boiling temperature of the three compounds using the data in the table and the Pauling electronegativity values in the data booklet. I'm telling you the electronegativity values, right? Just wait. That'd be
Just checking the data book the table.
First of all, you are supposed to consider like which one is polar, which one is non-polar, which one is having you can say permanent dipole, and which one is having the temporary dipole, and which one is having a strong dipole, which one is having the weak dipoles. First of all, you have to consider this. So if you can see, CH4 is totally non-polar. Am I right?
Yes, sir. Rest are polar.
Yes,
And
exactly. So, and then
H2O
water
is
is
less
having
polar
hydrogen
than
bonding.
HF.
Yes,
Though they
and
both have
HF is
hydrogen bonding.
also having hydrogen bonding. Number of electrons are equal. Interestingly, number of electrons are equal. So when the number of electrons are equal, so then what we are supposed to do, if you
The
can see the
polarity.
difference in electronegativity, so the difference of electronegativity of HF is higher, okay? And CH4 is having London forces, but the weak London force, okay?
Yes, sir.
According to the given boiling temperature, the water is having 100 degrees Celsius temperature as compared to HF, that is 19.5 degrees Celsius. So then what we are supposed to write? Why the water is having strong, like the high boiling temperature? This is very important thing in this question, basically. Hmm. And if you are going to
So is
consider
it
on the
because
basis
of
of
the
number of
polarity?
electrons, so I can
I
say
mean
that
the electronegative.
yes, exactly. They have the same London forces, the same van der Waals forces, because the number of electrons are same basically. Okay, if you are going to consider the number of electrons, but the thing is, weak intermolecular forces are present in CH4. Okay, and why? Because the difference of electronegativity is smaller, obviously. But the main point is that just straight away, I can say that CH4 is having London force, like I mean to say temporary dipole or van der Waals force, that is a weak force of attraction as compared to HF and H2O. But if we consider the both molecules, that is H2O and HF, okay, so hydrogen bonding would be there. But if you can count the number of lone pairs in H2O and also HF, like we always consider the central part, we always consider the central part basically, right? So water can form more hydrogen bonds as compared to HF. water can form more hydrogen bonds as compared to HF. So ultimately, I can say that H2O would be having strong intermolecular forces of attraction. Strong intermolecular forces of attraction. So first of all, number one, I would say that I would say that um, as they have the same number of electrons, so they all have the same strength of London forces. But H2O and HF both have hydrogen bonding. Both have hydrogen bonding. As their both have hydrogen bonding, but water can form twice hydrogen bonds compared to HF. Okay, so water is having strong intermolecular forces of attraction. So ultimately, more energy would be needed. More energy needed to, what should I write? More energy is needed to break strong intermolecular forces like this. This is H2O. This is another H2O. Okay. So this is the hydrogen bonding basically between the two water molecules. And since the water
Yes.
has two lone pairs, like oxygen has two lone pairs, oxygen has two lone pairs. If you draw the dot and cross diagram, so that's why I can say that water can form two hydrogen bonds, but HF can only form, one hydrogen bond. Okay, so that's why water is having the higher boiling temperature until until or unless both contain hydrogen bonding. It seems like that they would be having the same boiling temperature, but the thing is we have to count the number of hydrogen bonds. So after considering this, we would be able to know why the water is having high boiling temperature. Okay, right?
Yes, sir.
Okay.